What is the main motivation behind the creation of the ruler benchmark?
The main motivation behind the creation of the ruler benchmark is to evaluate long-context modeling capabilities for language models in a comprehensive manner. The benchmark was developed to go beyond simple retrieval tasks commonly used in previous works and assess behaviors such as multi-hop tracing, aggregation, and question answering. Ruler consists of synthetic tasks that offer flexibility in controlling sequence length and task complexity, reducing reliance on parametric knowledge that can interfere with utilizing long-context input in realistic tasks. By introducing new task categories and evaluating various long-context language models using Ruler, the aim is to provide a standardized platform for assessing and comparing models' performance across different complexities and lengths of context.
How does Ruler differ from existing benchmarks in terms of task types and evaluation criteria?
Ruler differs from existing benchmarks in terms of task types and evaluation criteria by introducing new task categories that go beyond simple retrieval from long context. It includes tasks such as multi-hop tracing, aggregation, and question answering, which test behaviors like CO-reference chain resolution, summarization, and question answering at various context sizes. Ruler evaluates models based on criteria such as the ability to retrieve information agnostic to the type of needle and haystack, strength in disregarding hard distractors, and high recall when multiple items need to be retrieved. This contrasts with existing benchmarks that primarily focus on retrieval-based synthetic tasks and do not cover a wide range of long-context understanding behaviors. Additionally, Ruler uses synthetic tasks that offer flexibility in controlling sequence length and task complexity, reducing reliance on parametric knowledge that may interfere with utilizing long-context input in realistic tasks.
Can you explain the criteria used to develop the 4 NEA tasks in Ruler?
The criteria used to develop the 4 NEA tasks in Ruler are based on 3 key aspects to evaluate the model's retrieval capability comprehensively. Firstly, the retrieval capability should be agnostic to the type of the needle and the haystack, ensuring that the models can effectively retrieve information regardless of the specific content. Secondly, the models should demonstrate strength in disregarding hard distractors, indicating the ability to focus on relevant information amidst noise. Lastly, the models should exhibit high recall when multiple items need to be retrieved, testing their capacity to accurately recall and retrieve various pieces of information from the context. These criteria guide the development of the single NEA, SNEA, multi-keys NEA, MK NEA, multi-values NEA, MV NEA, and multi-queries NEA, MQ NEA tasks within Ruler, each task designed to assess different aspects of the model's retrieval capabilities under varying levels of complexity and challenges.
What is the purpose of the variable tracking VT task in Ruler?
The purpose of the variable tracking VT task in Ruler is to emulate a minimal CO-reference chain resolution task to check the behavior of tracking relevant co-occurrence patterns and drawing skipped connections within long input. This task aims to evaluate the model's ability to recognize newly mentioned entities and establish chains of references co-referring to the same entity throughout the lengthy context. By initializing a variable with a value and inserting linear chains of variable name binding statements at various positions in the input, the task requires the model to return all variable names pointing to the same value. The complexity of the task can be increased by adding more hops or more chains, similar to adding hard distractors in other tasks like MK NEA. Ultimately, the variable tracking task assesses the model's capability to track relevant information and connections within a long context, testing its ability to maintain coherence and understanding across extended sequences.
How are the common words extraction (CWE) and frequent words extraction (FWE) tasks designed in Ruler?
The common words extraction (CWE) and frequent words extraction (FWE) tasks in Ruler are designed as proxy tasks for summarization. In the CWE task, words are sampled from discrete uniform distributions, with the number of common words fixed, while the number of uncommon words increases with the sequence length. The model is required to return the top k common words in the context, where k equals the number of common words. On the other hand, in the FWE task, words are sampled from a zeta distribution, and the model needs to return the top k frequent words in the context, with k set to 3. Increasing k in the FWE task leads to poor performance even at small context sizes for most models. The complexity of these tasks can be adjusted by varying the number of common words or the parameter of the zeta distribution.
What is the significance of adding distinct information to existing short context QA datasets in the question-answering category of ruler?
Adding distinct information to existing short context QA datasets in the question-answering category of ruler is significant because it allows for the evaluation of question-answering capability at various context sizes. By inserting golden paths, containing answers, into randomly sampled paths from the same dataset, this adaptation simulates a real-world scenario where questions need to be answered based on long context input. This setup mirrors the NEA test but in a more complex setting, where the question acts as the query. The golden paths serve as the S, and the distinct paths form the haystack. This approach tests the model's ability to sift through a large amount of information to accurately answer questions, showcasing its performance in handling long context scenarios.
How are the models evaluated in terms of inference setup and task configurations in the study?
The models in the study are evaluated in terms of inference setup by running the inference in bfloat 16 on 8 NVIDIA A100 GPUs with greedy decoding for all models. The study selects 10 long context language models, LLMs, including 9 open-source models and 1 closed-source model, GPT-4, covering diverse model sizes, 6B to 8x7B with MO architecture, and claimed context lengths, 32K to 1M. The evaluation is conducted using VLLM, an LLM serving system with efficient KV cache memory management. In terms of task configurations, the models are tested on 13 tasks ranging in diverse complexities from the 4 categories of ruler. Each model is evaluated with 500 examples generated for each length from the series: 4K, 8K, 16K, 32K, 64K, 128K, while complying with each model's necessary chat template. The task configurations are selected based on a task correlational study described in the appendix, ensuring a comprehensive evaluation of the models across different tasks and context lengths.
What is the effective context size, and how is it determined in the evaluation of the models?
The effective context size in the evaluation of the models is determined by GDING each model with a fixed threshold, which is based on the performance of the Llama 2-7B model at the 4K context length. If a model surpasses this threshold, it indicates satisfactory performance at that specific length of evaluation. The maximum length exceeding this threshold is reported as the effective length, along with the claimed length for each model. This method allows for a clear comparison of how well each model can handle different context sizes, and highlights any performance discrepancies between the claimed and effective context lengths of the models.
How are the models ranked and compared in the study using weighted average scores?
The models in the study are ranked and compared using weighted average scores by aggregating model performance across various context sizes. 2 weighting schemes are employed: WAVG, Inc., and WAVG, DEC. In the WAVG, Inc. scheme, the weight linearly increases with sequence length, simulating scenarios where longer sequences dominate the distribution. On the other hand, in the WAVG, DEC scheme, the weight linearly decreases with sequence length, simulating scenarios where shorter sequences dominate the distribution. These weighted average scores provide a more nuanced and detailed comparison of model performance across different context sizes, allowing for a comprehensive evaluation of how models perform as the context length increases. The top models, GPT-4 Command R, Ye34B, and Mixtel consistently outperform other models, regardless of the chosen weighting scheme, showcasing their superior performance in handling long context tasks in the study.
Can you elaborate on the failure modes observed in the analysis of Ye34B200K model in the ruler benchmark?
In the analysis of the Ye34B200K model in the ruler benchmark, several failure modes were observed. Firstly, the model exhibited non-robustness to different types of needle items, showing a significant drop in performance when retrieving UUIDs compared to word number pairs. This led to incomplete answers, especially with longer input contexts exceeding 128K tokens. Secondly, Ye34B200K struggled to ignore distractors effectively, with performance steadily decreasing as the number of distracting items increased. In extreme cases where the context was filled with distractors, Ye34B200K had difficulty in filtering out irrelevant information, resulting in incorrect retrievals. Additionally, the model returned incomplete information when tasked with retrieving multiple items from a long input, often outputting duplicated answers without providing the complete set of values associated with a key. Furthermore, Ye34B200K displayed a tendency to copy verbatim from the context as the input length scaled up, particularly noticeable in tasks like variable tracking and common words extraction. This behavior was less prevalent in other models, like Mixtel. Lastly, Ye34B200K showed unreliable tracking within the context, struggling with tasks that required tracing the same entity across long sequences, especially when adding more chains or hops. These errors were also observed in models that did not exhibit the copying behavior, indicating a general difficulty in reliably tracing entities within long contexts.